Now we are switching over to the second lecture entitled Charge Density Analysis and Fundamentals of Magnetic Superexchange, given by Roger Johnson from University College of London. So Roger is a lecturer in condensed matter physics at the University College of London, having recently moved from University of Oxford, where he held a Royal Society University Research Fellowship in the Department of Physics. Roger works in the area of quantum materials and physical crystallography. Crystals and magnetic structure solutions are usually obtained by multiple diffraction-based methods and combined with symmetry analysis by group and representation theory. And he determines structure property relationships in inorganic oxides, halides, and hybrid organic-inorganic materials. Roger?
Thank you. Can you hear me okay?
Yeah.
Great. I'll just okay, can I close this?
Yeah, now we are seeing.
Yeah. Okay, very good. Well, thank you very much for the introduction. And thank you, Paulina and Christoph, for this fantastic opportunity to talk to you and the community here today. I was very excited to share some of our results with everyone working in this area. So as you said, I've been asked to give the complementary talk here. I'm not an expert in charge density analysis, as Piero obviously is, but our group is moving towards this direction to see how we can use this technique to understand more about, in this case, magnetic superexchange in certain materials. So first, I'd like to just acknowledge those people I've worked with on this project. Firstly, I must mention Dr. Rebecca Scatina. A lot of her work has gone into the results that I will present towards the second half of this talk. Rebecca did her PhD at the University of Bern under Piero's supervision, and I've been very grateful for the support of both of them in this area. I'll present some high pressure studies that were performed by Mikhail at the University of Bern, and I'd like to also acknowledge Pascal Manuel and Dimitri Kalovin, who are instrument scientists at ICIS, the UK neutron and muon source. I also just acknowledge the Royal Society and the SNF for funding of this work. Okay, so just to give a brief outline, I come from a community really working on fully inorganic systems. My particular attention has been drawn to the transition metal perovskites. So I'll give what I think are some interesting examples from this field before moving on to a description of, if you like, a rules of thumb to describe magnetic exchange in these fully inorganic materials, the so-called Goodenough-Kanamori-Anderson rules. I'll then introduce some new systems and new directions that we're going in, the so-called hybrid organic-inorganic perovskites, analogues of the inorganic systems. These are often known in the literature also as coordination polymers or molecule-based magnets, or indeed sometimes MOFs and metal organic frameworks. This can be used kind of synonymously. And I want to focus on some advantages of these systems with regards to their building block character and some unconventional degrees of freedom. And then I'll move on to the actual material in question that we've studied using charge density analysis, and that's dimethyl ammonium copper formate 3. Okay, so the family of materials that I'm going to focus on this talk are the perovskites. So these, I'm sure many people in the audience are familiar with the perovskite framework, but just to summarize briefly here, it has a chemical formula ABX3. A and B are cations. The A site is colored green in this figure here. The B cation is octahedrally coordinated by the X site, which is often oxygen. These are often transition metal oxides. And a vast number of material properties have been discovered in the perovskite framework. They're an incredibly versatile system, from multiferroics, piezoelectrics, ferroelectrics, spintronics, and colossal magnetoresistance. And perhaps one of the reasons for this wide range of properties is that the structural framework is incredibly flexible. I've just copied at the bottom here the so-called Goldsmith tolerance factor, where essentially RA and RB are the radii of the A and B sites, and Rx is the radii of the X site. So for systems where A is large and B is small, the tolerance factor goes greater than 1. In this case, this system tends to remain cubic. The B site can become underbonded, and we can see instabilities towards ferroelectricity, as we see in, for example, barium titanate, quite famously. Or when A is small and B is large, then the tolerance factor is less than 1. And then what we see is a well-characterized set of octahedral tilts and rotations at that onset in order to accommodate the smaller cation at the A site. And the tolerance factor can actually go quite a way below 1 and still remain a stable phase. And one of the appealing things about this framework is that it lends itself to kind of a fundamental phenomenological symmetry-based approach to understand the coupling between these different structural degrees of freedom and the various phenomena that can emerge. So it doesn't stop just with the ABX3 systems. There also exist double perovskites. These are materials where you have two different elemental species at the B site that form a kind of rock salt ordering, as I've drawn here. There are the so-called quadruple perovskites, which I spent quite a bit of time working on, where we have a 1:3 ratio ordering at the A site. And then more recently, we've done quite a bit of work on the so-called columnar-ordered quadruple perovskites, where the A site is in fact split into 3 different symmetry and equivalent sublattices that form columns running along the C-axis. So the structural flexibility really goes a long way beyond the simple perovskites. Okay, so I just wanted to introduce some interesting concepts that appear with a particular focus on magnetism. So one of the things that one can do with this framework is alien-valent tuning. So we can mix a 3+ cation, for example, praseodymium here, and a 2+ cation, calcium, at the A site. And in doing so, we can tune the oxidation state of manganese at the B site. And then we get these really extensive phase diagrams appear, which are incredibly rich as far as the magnetism is concerned. So we can just focus on the 1/2 end here, the so-called CE magnetic phase. And I've just drawn diagrammatically what happens in the material. We get a charge ordering at the B sites. The oxidation state is normally +3.5. It segregates into 3+ and 4+. This is then accompanied by some orbital ordering, where the 3+ ions have a Jahn-Teller instability that I show with this single D3Z² minus R² orbital in the figure. And then we have this complex extended zigzag type magnetic order at low temperature. We can actually create similar effects in the quadruple perovskites as well. So here, for example, we have sodium and calcium at the A site. This solid solution spans the same range of B site oxidation states. And we see actually the same CE phase is stabilized, but remarkably in this system, because we have additional manganese at the A site in the quadruple perovskite, we find these very complicated incommensurate type structures that can appear for certain compositional ratios of sodium and calcium. If we keep going all the way up to calcium Mn7O12, the system with no sodium, we enter into this helical phase on the right-hand side of this phase diagram. That's the subject of my next slide. And in this material, this is a really remarkable material because this undergoes a cubic to rhombohedral charge ordering phase transition, where at the B sites we have 3 manganese 3+ for every 1 manganese 4+. And then on further cooling below about 250 Kelvin, we see an incommensurate structural modulation setting. And this incommensurate structural modulation can be understood in terms of an incommensurate variation in the occupation of, for example, a 3D x² minus r² and a 3D y² minus r², which I've shown in kind of cartoon form in this 1D chain for when it goes from blue to green to blue, interleaved by a square planar coordinated manganese 3+ at the A site. And then at low temperature, this is accompanied by a helical magnetic structure. And this helical magnetic structure, again, is quite unusual. It doesn't have a continuous pitch. In fact, the relative angle from one spin to the next is modulated throughout the crystal. And that phase, if you like, the angle between the spins modulates with the same periodicity as the incommensurate orbital structure itself. So again, an interesting case that emerges from this perovskite families when we can play with the chemistry. Okay, going to another example from the inorganics that I want to talk about is that despite having, what is really a well-connected, dense, three-dimensional framework, we can find low-dimensional magnetism. And this is a particularly interesting case in point, potassium, copper, fluorine 3. And we know we have low-dimensional magnetism because it's characterized by this very broad hump in the magnetic susceptibility, where essentially the central position of this hump is characteristic of the dominant one-dimensional exchange interaction in the material. Nonetheless, this does actually order at low temperature. The magnetic structure was determined, and it also has this accompanying orbital order, where what's drawn here is the partially occupied dx squared minus y squared orbital of copper in the system. Okay, so the question is, can we reconcile this different magnetic behavior in terms of the structure, in terms of the orbital structures that we've seen? I've very deliberately drawn the orbitals alongside magnetism. And so here enters the Goodenough-Kanamori-Anderson rules, because they provide us really with rules of thumb to understand this coupling between orbitals and magnetic exchange. And these rules were really developed from out of this area of the Fully-Inorganic perovskites. So I just wanted to introduce them to you briefly now. The two fantastic books, Goodenough's book, Magnetism and the Chemical Bond, and Daniel Komsky's recent book, Transition Metal Compounds, they really go through all of the details here. I just take some results from those texts. So if we just define the exchange interaction, the Hamiltonian in the top right here, where H is J times the sum over SI dot Sj, essentially J here is an exchange parameter. Si and Sj are the spins on nearest neighbor sites I and J. So if J is positive, then this energy will be minimized for anti-parallel spins. So J is considered to be an anti-ferromagnetic interaction. And if J is negative, then this energy will be minimized for aligned spins, and J is then considered to be a ferromagnetic interaction. So if we have direct exchange, let's imagine here we have two d orbitals that are singly occupied, and they overlap with each other. Then the Pauli exclusion principle from this hybridization requires that these two spins are anti-parallel in the ground state. So here we get an effective anti-ferromagnetic exchange interaction, and J can be written to reasonable approximation as T squared on U, where T is some measure of the ability of the electrons to hop between the two sites. This is the measure of the degree of orbital overlap, and U is the Coulomb repulsion that we'll be familiar with. In the same scenario, but if we had an unoccupied orbital, which is represented by this dashed line at the bottom here, then what happens is essentially that the single electron that's singly occupied on the left just hops over virtually, spends a bit of time in that orbital, Huns couples to the rest of the magnetic the unpaired spins on that atom, and then hops back again. So this gives rise to an effective ferromagnetic exchange interaction. So we have now minus T squared on U, but it scales with this Huns coupling local to the ion. We can go one step further, and we can put an oxygen atom in the middle, and this is what's known as superexchange. So if we think about superexchange on a 180-degree bond, the spins are still largely localized in this system, but we might think that we've got a problem, because we might think that these two paired electrons in the middle here create, if you like, a magnetic block between these two atoms. We have this non-magnetic oxygen p orbital in the way. But what actually happens is that the energy of the system is lowered if these electrons can be deconfined, if they can hop across the bond. And so we can concern ourselves with the excited state, and what we can show is that if, for example, the spin up electron on the oxygen can hop over to the d orbital on the right, which will be possible if that spin is down, then the spin up electron on the left will hop into its place on the oxygen in the middle here. So essentially, if we have anti-aligned spins on the d orbitals, that facilitates some degree of hopping across this bond, which ultimately lowers the energy of the system. Our exchange interaction becomes slightly more complex, but all I wanted to point exchange parameter, sorry, all I wanted to point out is that still it's proportional to this hopping t squared. We've got 1 over u in here. The Coulomb repulsion is against the process, and then what turns up is this delta CT, which is essentially the charge transfer gap, which is the energy cost of moving the electron from a d orbital into the oxygen. So this wasn't present in the previous case. And then if we go to the next example where we have an unfilled orbital, again, this is shown by this dashed line here, we could apply a similar logic, and essentially what can happen is a spin-up electron can hop from the oxygen into that orbital. That can then Hund's couple to the rest of the unpaired electrons on that site, and then the spin-up electron on the left can then hop into the oxygen in the middle, and vice versa. So we have here an effective ferromagnetic exchange. So it largely mirrors, actually, if I just flick back, the results that we obtained from the direct exchange case, but we just have it scaled differently. Okay, we can just go one step further now with Hund's rules, the GKA rules, and we can think about the interaction on a 90-degree bond. And what we have here is very similar logic applies, but now the interaction occurs via 2 oxygen p orbitals. So we end up with what is effectively a ferromagnetic exchange interaction, where we rely on a Hund's coupling between the electrons on the p orbitals. Like I say, that's a summary of the GKA rules, and these 2 textbooks really give a detailed description. But if we go back to these examples that I gave at the start, they do work. So we've got a charge order in this 50% system. This leads to this orbital order. And then what we can see is that when we have an occupied magnetic orbital, the dz squared minus r squared pointing towards a non-magnetic orbital, we have a ferromagnetic exchange interaction. And when we have essentially what will be a T2G facing a T2G, we have an antiferromagnetic exchange interaction. So it well explains this correlation between the orbital order and the magnetic order. In the case of this complex incommensurate phase modulated helix, we can actually apply similar rules, in that we can understand that as the orbital occupation modulates throughout the crystal, so does the nature of the exchange interaction that can then give rise to this phase modulation, where some regions of the magnetic structure are more ferromagnetic, if you like, and some regions of the magnetic structure are more antiferromagnetic as a result of this shift in orbital occupation. And we can also understand why we get one-dimensional behavior in potassium copper fluoride, because what we essentially have is we have the case that we have a singly occupied orbital facing a singly occupied orbital along the c-axis, making chains. So we have strong antiferromagnetic exchange interactions along these c-axis chains. But then we have a magnetic orbital facing a non-magnetic orbital within the plane, giving rise to essentially negligible exchange interaction in that direction. So far so good. The GKA rules tend to work pretty well. Okay, so now I want to move things forward into the hybrid organic-inorganic perovskites. And the reason we're moving in this direction is threefold, really. Is one, I want to show you in the next slide that they can form model quantum magnets. We've got this kind of building block control over the framework, so we feel that we could kind of engineer particular properties into these systems. And there are also unconventional structural degrees of freedom that aren't present in the inorganic systems, and I'll introduce those as well. But also more importantly, and I suppose that's why I'm here today, is that as Piero pointed out in his talk, charge density analysis is applicable in the study of these systems. So where all of the orbital pictures that I've drawn before are basically cartoons inferred from bond lengths determined by conventional diffraction techniques, in these materials, can we design and model quantum magnets? And can we make an experimental determination of the charge configuration that is mediating the exchange exactly as we want to see? Do the GKA rules still work? Do they still hold when we replace a single oxygen p orbital with a whole molecule? Or are they in some cases violated? So these are the kind of questions that we want to work, and the results I'm going to show you now are working towards answering those questions. Okay, so what do I mean by model quantum magnets? So just to give a few examples, compared to the inorganic materials, one of the advantages of these systems is that the distances tend to be quite large. So the inorganic materials are all often complicated by next nearest neighbor interactions, next nearest neighbor interactions, etc., etc. I show on the left here a simple 2D lattice where we have nickel coordinated by pyrazine, and to very good approximation, we can consider just the exchange interactions on this square lattice. And this gives us a model system in which, as Jamie Manser did in this paper, can explore the way in which one can tune anisotropies at the nickel site, because it creates a model system in which we can have a handle on one particular aspect of the magnetic properties. Another case here, we can create these so-called chiral chains. So this is arguably one of the most one-dimensional magnetic materials that's known. And in this case, we can worry about the effect of the chirality on the magnetic system and the fact that we have we build in staggered fields from G-tensor anisotropy. And in this particular case, it gives rise to very exotic excitations, magnetic excitations that can travel up and down the chains. This is with copper bonded by pyrimidine, and then on the right here I just give another example of copper formate to tetrahydride, and this is one of the most two-dimensional materials, arguably, that's known in terms of magnetic ordering, by virtue of the fact that the magnetic exchange is almost negligible through these hydrogen bonds between the waters, between the planes. And in this example, this is a beautiful example of a two-dimensional magnetic system where there has been observed fractional excitations, if you like, the 2D analog of spin-ons that are found in 1D chains. So there's lots of interesting aspects of these systems from a magnetism point of view. What do I mean by building blocks? It's been said that one of the advantages of these systems is that if we understand the way that formate behaves, it will always behave in the same way. So we can start to characterize the individual components of these systems, and we can create materials under the assumption that their properties will be essentially a sum of their parts. Okay, is this true or not? That's something that we should explore, and it's some part of the work that we're doing now. And finally, unconventional degrees of freedom. Just to summarize briefly, in inorganic systems, we have corner-shared octahedra sharing a single oxygen atom. So if one octahedra rotates anti-clockwise, then its neighbor must rotate clockwise. Okay, if these octahedra are now connected by a ligand, for example, formate, then we can introduce new structural degrees of freedom into the system. For example, octahedra that rotate in the same fashion, or we can have columns that shift past each other linearly, or we can have planes that shift past each other. So, what is the effect of these different degrees of freedom on the material properties? Right. So let's move on to then dimethylammonium copper formate, and I want to summarize the work that's published in this recent paper authored by Rebecca. So formate-mediated magnetic superexchange, and do the GK rules still work? So this material has the perovskite structure. So essentially we have copper that's octahedrally coordinated in a pseudo-cubic framework, and instead of oxygen we have formate anions in every direction, and then essentially the space is filled and the charge is balanced by a dimethylammonium ion at the A site in the center here. Okay, the copper is Jahn-Teller active. The octahedra wants to extend. It does so. This is seen in conventional diffraction, and this then actually creates an orbital structure that is a very good analog to the potassium copper fluoride case. That's what we would predict based upon bond lengths alone. It gives rise to two different exchange pathways. Along the C-axis, we have these, what we label here, equatorial bonds. So these are, if you like, the direction in which we anticipate the magnetic orbitals to lie, creating strong magnetic exchange pathways along C. And then in the AB plane, we have these so-called equatorial axial bonds, which are these asymmetric bonds between the Jahn-Teller axis and non-Jahn-Teller axis. So first we did magnetometry, and what we see is much like the case of potassium copper fluoride. We see a broad hump in the magnetic susceptibility. So this is indicative of one-dimensional ordering as we anticipated. But there is a low temperature phase transition at 5.2 Kelvin. We can fit the so-called Bonner-Fisher model for a 1D spin half Heisenberg antiferromagnet, and we can extract a value for the exchange interaction along that chain. We've also done single crystal magnetometry, where we measure essentially the magnetization of the sample as a function of magnetic field. What we see here is we see a linear dependence along B and along C, This is characteristic of an antiferromagnet where the magnetization is originating in essentially a field-induced spin canting of the antiferromagnet, and this linear gradient is, if you like, a measure of the stiffness of the system, the strength of the exchange interaction that would rather the magnetic moment stayed anti-parallel. We can derive a simple model where J appears in the denominator. We can fit the gradient and we can extract again an exchange interaction of about 72 Kelvin. So in good agreement with the susceptibility data. We also see this little wiggle occur at about 0.7 Tesla. This is indicative of the antiferromagnetic moments lying along the A-axis, and this would then be a so-called spin-flop transition, where the critical field BC is some measure of the anisotropy energy that's keeping the magnetic moments in that direction. We used neutron powder diffraction to then explore the magnetic structure further. Here I've plotted the data measured at 1.5K with the 10K data subtracted away, the paramagnetic data subtracted away, and we see these magnetic Bragg peaks. We can fit these magnetic Bragg peaks, and what we find is that we have an antiferromagnetic aligned spins along the C-axis, which are then ferromagnetically aligned in the AB plane, so a so-called A-type magnetic structure. So it seems then that formate is mediating both antiferromagnetic exchange and ferromagnetic exchange in this material. So can we go deeper into the nature of this exchange interaction? And we did this through a charge density refinement. So there was a plot similar to this in Piero's talk, looking at the residuals. So the data were collected on a laboratory source, if I remember correctly. Something of the order of 41,000 reflections measured out to a resolution of 0.44 angstroms. And if we use just an independent, a conventional independent atom model, then we can find an R factor of about 2.89. But if we look at the residuals, there are two things that are telling. One is that I'm looking now at the top plot. The width of this is reasonably large and the peak is quite high, but it also doesn't follow this normal distribution that one might expect. So this points towards there being some discrepancy in the residuals. So we introduced then a multipolar model that was expanded up to the hexadecapoles, at least for every atom other than hydrogen. We refined kappa and kappa prime, the expansion parameters that Piero described, and we find an appreciable drop in the R factor down to 1.35. And we see a much tighter distribution of the residuals, which are distributed normally. Okay, so we're confident that we've done a good job of the charge density refinement in this case. So let's look at the results. So if we look at the ligand first, so the charge density results are shown on the top right here, and on the top row is the equatorial configuration, which is observed to be antiferromagnetic, and in the middle row is the equatorial axial configuration, which is found to be ferromagnetic. And what we see is the charge density on the formate is remarkably similar, qualitatively at least, in both cases. So it seems like the formate electronically is the same in both scenarios. The difference really occurs just in the nature of the bond to the copper. And what we see is essentially a more ionic character of the bonding to the axial copper on the right-hand side and on the bottom row. And we can quantify these differences by looking at the bond critical point and plotting essentially the charge at that critical point and calculating the Laplacian. And what we see is that if we look at the oxygen and oxygen-carbon bonds, the first thing we see is that the quantities were very similar for the two formates. These numbers are characteristic of essentially a covalent type bond where there is appreciable electron density localized on the bond. And we also see similar parameters for the copper-oxygen bonds, which are here more coordinative in character, with the copper-oxygen 3 bond being the most ionic, let's say. We can also subtract the charge density evaluated for the equatorial axial formate from the equatorial formate, and we find a difference of just half electron across this whole formate structure. So, with the view to apply the Goodenough-Kanamori-Anderson rules in mind, we can move forward under the assumption that these two formates, electronically at least, appear to be the same, and that's a result that we wouldn't have got without this charge density analysis. we can take a look at the transition metal, the copper, and what I've plotted here are deformation density maps. So this is, if you like, the result of the multipolar model with the spherical distribution subtracted away, such that the blue corresponds to additional charge density in the system with respect to the spherical model, and the red corresponds to a deficiency of charge with respect to the spherical model. And it's really beautiful. What you see appear is you see these dz squared minus r squared orbitals, or shapes that look like those orbitals appear along z in the blue, which we anticipated to be doubly occupied. And then on the left-hand figure here, we can really see the dx squared minus y squared orbital in red, which has only got 1 electron in it rather than 2. These Piero highlighted the difficulty in mapping between the orbital occupancies and the charge density, because the charge density is the square. Well, not only is it hybridized with everything else, but it is in the square of the orbitals. But in the case of a coordinated atom where the charge is largely localized on the transition metal, we can do a reasonable job of it. And this mapping was done in this case, and we can see that the x squared minus y squared orbital is roughly half full with a single electron, whereas all the other d orbitals are fully occupied with 2 electrons. So this paints the picture that we expect for this Jahn-Teller distorted copper atom. So if we bring these 2 charge density results together, then what we essentially find is that the Goodenough-Kanamori-Anderson rules seem to work very well, despite the fact that we've replaced oxygen for formate. That is to say, we can treat every formate electronically the same, and what we see is strong antiferromagnetic exchange in the equatorial direction, where we have our half-occupied x squared minus y squared orbitals pointing towards each other through the formate, and we have very weak ferromagnetic exchange in the direction where we have the doubly occupied z squared minus r squared orbital pointing towards the formate here. So if we just take this one step further and we think more generally about the GK rules, then we proposed essentially a Maxwell set of criteria for the ligand, such that it essentially emulates the role of oxygen in such a framework. And these were that the highest occupied molecular orbital that will mediate exchange must span the whole molecule. It must have an appreciable electron density on the extremal atoms that coordinate the metal, and it must be symmetric about the middle of the molecule. But these are all points that we want to test, and we want to explore this further in more and more complicated ligands. But baby steps first, and the approach that we're taking at the moment is to stick with what we think are going to be symmetric molecules, so pyrimidine, formate up to the nitrate, but we're going to vary through the spectrochemical series of these ligands and see what we see, and see if we can do the same charge density studies and see if we can build up a robust picture of the nature of the electronic configuration of these systems. Okay, may I ask how much time can I talk for? This is another.
Yes, please continue. I mean, we are not that strict on time.
Okay, that's great. Thank you. Okay, so I now want to move on to another aspect of this work, sticking with the same material, but instead a study of the system under high pressure, and this links very nicely into Piero's talk first in this session. And indeed, charge density analysis is something that we would like to do on the system under high pressure. So I tried to stress that the dimethylammonium copper formate is, if you like, a hybrid organic-inorganic analog to the well-known potassium copper fluoride, the fully inorganic system. So what happens to potassium copper fluoride under high pressure? So this is a study from 2011. On the right here, I plot the copper fluoride bond lengths. And what we see, very similar to what Piero mentioned, is that the softer bond, the Jahn-Teller elongated bond, compresses. And it moves down and down and down until it reaches a similar value to that of the equatorial bonds at 8 kilobar. So essentially, we're just suppressing this Jahn-Teller distortion. And what the nature of this orbital state is up at high pressure is an open question. It's something that was raised by a member of the audience. So there's no transition observed. However, so So given this, high pressure X-ray diffraction studies were performed in diamond anvil cells on the dimethyl ammonium copper formate system. Here we've got these nice pictures to show the sample well loaded within the gasket of the diamond anvil cell. And these measurements were done by Michael and colleagues at PSI. So what was observed? Essentially, we get a volume contraction as we might expect, and then that's around 6 gigapascals, there's a collapse in the volume. And if we then solve the crystal structure above and below this phase transition, we see a transition from a monoclinic crystal structure at low pressures that I described previously to a very different triclinic structure at high pressures. And if we focus now just on the orientation of the yarn-teller axis, what we find is that 2 of the copper sites, roughly speaking, maintained their orientation of the yarn-teller axis. The reconfiguration of the structure is quite severe, so I can't say exactly the same, but roughly, whereas 2 of them have rotated by 90 degrees, to good approximation. So we can consider this phase transition to be a yarn-teller switch, if you like, induced a function of pressure that, I stress, was not observed in the fully inorganic material system. So the approach that we took to try to understand what's happening at the level of the structure is to perform a modal decomposition of both structures with respect to some hypothetical high symmetry parent. So what this means is it means that we take a high temperature structure where, for example, all of the octahedra are cubic, they are all upright and well aligned. In this particular case, this would have been in a tetragonal symmetry. And then what we can do is we can then do a decomposition of the true structure in terms of the amplitudes of these modes. And these are modes that are symmetry adaptive modes that are allowed within the symmetry in question. And what we plot then is we plot the evolution of these modes as a function of pressure. And this is informative because it gives us some understanding of how the fundamental normal modes of the structure are responding to the high pressure. So on the left here, I've plotted the conventional tilts. And what we see is that they persist up to high pressures, but we see a small collapse in one of the rotations of the octahedra around one of the axes. Okay. With regards to the unconventional tilts, however, is that despite them being allowed, or at least one family of them being allowed in the low pressure phase, as I alluded to in the previous slide, it appears they really switch on at this phase transition. So they become large and significant in this triclinic phase that appears at high pressure. So in this case, I'm describing octahedral rotations that co-rotate with each other, which wouldn't be allowed in the inorganic system. We can then look at the yarn-teller distortions. Now, we can consider these to be conventional, essentially. These would be allowed in the inorganic case. And again, there is clearly a striking reconfiguration of the yarn-teller distortions. And on top of this, what you can kind of tell with the black line here is that we have this reconfiguration, but we also have this kind of global reduction of the yarn-teller distortion. So it is responding in a similar way to the potassium copper fluoride. We do see a reduction in the amplitude of this mode, but we still have this very large reconfiguration that occurs at about 6 GPa. And then we can look at the columnar shifts and planar shifts. These, again, are unconventional modes of the lattice with respect to the inorganic. And we see very much that these switch on in the triclinic phase. So the way we interpret these results is to say that, we take the observation that this phase transition has not occurred in the inorganic system, but it has occurred in the hybrid organic-inorganic system. We infer then that the reason this transition can occur is because these unconventional structural distortions are allowed in the hybrid organic-inorganic system where they were not in the inorganic. But we can actually look slightly closer at the problem and what the implications are of these unconventional modes with regards to the bonding to the formate. And just by observation, a lot of the perovskites of this structural form have formate bonded in anti-anti fashion. which I've drawn on the right-hand side of the figure here. However, if we introduce these unconventional rotations of the octahedra, then that's going to push the formate towards a syn-anti type bonding configuration. So if we work under the hypothesis that for some reason the formate wants to bond anti-anti, and it costs energy to be syn-anti, then we can understand the nature of the energetic competition leading to this phase transition. That is to say that the steric contraction of the lattice through and the volume contraction from high pressure wants to create these unconventional rotations. They're degrees of freedom that the system can explore. The resistance to those deformations is originating in the desire for formate to be bonded anti-anti. This is a hypothesis. This would be something that would be interesting to explore in the future. And of course, the other implication of this phase transition is that it in principle has a profound impact on the orbital and magnetic reordering. We've called it a yarn-teller switch before. That's based upon the bond lengths. Presumably, the orbital configuration will follow. And if the orbital configuration follows, then presumably the magnetic structure follows via these GK rules that I discussed before. But I think this would be a particularly interesting case to explore then with charge density analysis again. Because while it seemed to give what perhaps one might consider to be the obvious result under ambient conditions, I don't know if it's so obvious where the electrons or where the charge is going to go under high pressure in this metastable phase. And also it'll be interesting to do neutron diffraction to explore the nature of the magnetic order in this phase as well. So they're all kind of jobs to be done, if you like. But as Piero explained, they are challenging experiments to do under high pressure. But hopefully we'll have the opportunity to answer both of these questions in the not too distant future. So I'll just to summarize. I started off by introducing some background in the inorganic magnets, but I hope I convinced you that there's good reason to pursue these kind of physical problems in the hybrid organic-inorganic systems, if only because we can do charge density analysis to look at the interactions at an unprecedented level of detail beyond the kind of cartoon drawing of the orbitals. I focused on dimethylammonium copper formate 3. We've shown that it had a type A magnetic structure, that is, and in this structure, formate is mediating both ferromagnetic and antiferromagnetic superexchange. But importantly, the charge density analysis shows us that electronically, all the formate is basically the same. We determined the orbital structure of the transition metals from charge density analysis, and we've found that the GK rules do indeed hold in this case. We've discovered a pressure-induced phase transition, which is, if you like, characterized by a yarn-teller switch, and we make predictions then about the nature of orbital ordering and the magnetic structure. And just very briefly looking forward, as I have said, we could really extend this study into how we can systematically control magnetic superexchange through the choices of our ligands. What if we have asymmetric ligands? What if we functionalize the ligands? What if we can gate the ligands in some fashion? And explore all of this at the same time with charge density. Will the GK rules keep working for us? Or will at some point they break down and the situation just becomes more complex when we have to worry about the nature of molecular orbitals and the way in which the magnetic exchange interaction occurs? And as I said, it'll be really great if we can push this further into high pressure studies. And with that, I'll thank everyone very much for their attention.
Thank you, Roger, for a beautiful lecture and a very clear lecture. And now it's time for questions. Please type questions in the chat or raise a hand. In meantime, I have a question. How easy is this to obtain such a crystal, and how stable they are?
Sure. So if you don't mind, I'll speak on behalf of Rebecca, because I must stress that Rebecca has chemistry training and really is the expert in synthesis and charge density. So these materials are grown out of solution. And a lot of them are grown under solvothermal conditions. So once the recipe and conditions are established, they tend to grow very well. And importantly, because they're growing out of solution, the crystals tend to be highly pure. Some of these frameworks are inherently prone to disorder, particularly when you have a molecular unit at the A site, which could have a lower point symmetry perhaps than the point symmetry of the framework at that site. So you can have positional disorder at play there and things like this. So some of these systems, they don't order well. As it happens, the dimethylammonium copper formate does order very well and does form beautiful crystals. And that's one of the reasons, of course, that the charge density studies work particularly well.
So these are like a basic science investigation. Do you see any applications already for those materials you crystallize? Right.
So the ones that we're working on at the moment, we are very much interested in them at a fundamental level. So there is work being done on multifluorics in this area. So these are materials in which the crystal is polar, ideally ferroelectric, and has switchable polar domains, and is also magnetic. And there is some cross-coupling between the magnetism and the ferroelectricity. And this can occur in one of two ways, actually. Either you can have a material that is polar that magnetically orders, and then the magnetism inherent some signature of the polar domain that it lives in, or you can have systems in which the magnetic structure itself breaks inversion symmetry and thereby directly couples to the polarization. And there are some interesting work being done on very similar frameworks to these, actually. So if you have manganese and cobalt, methylammonium as an A-site countercation, there's some work being done in this direction. One disadvantage at present is that the interactions tend to be weak. From a fundamental point of view, it's a great advantage. It means you can push them around with small magnetic fields, you can push them around with relatively accessible pressures, and it means you can study simple models, as I suggested. You don't have to worry about very long-range interactions. But any application, you want to happen at room temperature, right? So yeah. This is an issue here, but we're thinking about this, and there are ideas and routes to where we might be able to enhance different nature of the exchange through these different ligands, to explore choosing to increase these exchange interactions if we can.
Do you see any possibility also to apply high pressure for to construct such a device in which a pressure is also applied, not only temperature, to find the proper working condition, or it's not? So
sorry, would you mind asking that again? So what?
Yeah. So you said that at the moment, if you would like to design some device working on these materials, you would need to lower temperature, right? Because the interesting properties are lower temperature. How about playing with pressure?
Absolutely. I mean, so this Yarn-Teller switch was observed at ambient temperature under applied pressure. So yes, absolutely. Maybe there are sensing applications or environments in which such a device could operate under high pressure conditions. I fully agree. And one could also explore the way in which the pressure is applied in order to make the device functional. What can we do with chemical pressure, for example? Can we include these things in heterostructures, more complex material systems? Can we combine them with piezoelectrics? Can we strain them? Et cetera, et cetera. Yes, I think there's a lot of interesting work to do there. Absolutely, yeah.
Mm-hmm. There is a question from Hansbit. Do you see diffuse scattering near the phase transition? If so, are they in the right place, in the BZ, inelastic scattering maybe?
So is this magnetic diffuse scattering? Is this with regards to the magnetic phase transition or the?
I was thinking of phonons, because you have all those various kinds of rotations. and some of them may actually become soft phonons, but it was so complicated I couldn't figure it out in the short time.
Right. Yeah, I think that's a great suggestion. The answer is I don't know. I don't know if the data are sufficient measured under high pressure to look for diffuse scattering, but I think the suggestion that one might study the role of phonons in this phase transition, and like you say, the dynamical modes associated with these degrees of freedom, I think is a very good one. Maybe one could also do some Raman in a high pressure cell or something like this to explore that if it's too difficult to see in the diffraction. Yeah.